Okay, today is really beginning of the second half of the course. So until today, we were busy building our basics of what is matrix and what is vector space and column space and all subspaces and what are those and everything. Now we will start using those and see what we can do with matrices, and we will start picking up the fruits of it. So the length of a vector you are all familiar with this two-dimensional space. If I give you a vector v with component x and y, what is the length of this vector? What is it? What is the length of this? So x squared plus y squared. So I call this square of it is equal to this, right? This is called the Pythagoras rule. Okay, so in general, in n-dimensional space, when you have a v is equal to x1, x2, xn, okay? So this is called the length of v, okay? And square of this is equal to x1 square, xn square. Okay, this is called the length of a vector. So it's a generalization of what we know from two-dimensional case. Okay. We also used this before, but let me formally define it. If you have a vector x, x1, x2, xn, and you have a vector y, y1, y2, yn, x dot product y is called, this is x transpose y, okay? So this is dot product. What is that? x1, xn times y1, yn, which would be x1, y1, x2, y2, xn, yn. Okay? This is also called inner product. Dot product, inner product. Sometimes we show it like this, okay? So this is the same thing. What is this? Is this a vector or a matrix or a scalar? What is this? Scalar, right? Okay. So therefore, if I take transpose of this, what would I get? It would be y transpose x. Of course, it is the same as x transpose y, right? So inner product or dot product of two vectors doesn't change if you x dot product y or y dot product x, they are both equal. And unfortunately, we only have a third of the class here. And this shows us what's going to the trouble you will have in the final. Okay. Now, we want to see what is Pythagoras rule. So what do we call these two vectors? This is, let's say, this is x vector, this is y vector. What are these? What do we call them? Perpendicular, right? This perpendicular vector. So this is a right angle. That's why when it is right angle, then if for example x was this, then it wouldn't be x squared plus this. So this x is just x and y, they are just right angle here. That's why this is true. Now let's talk about if I have a vector x and vector y in Rn. So in the n-dimensional space, I have two vectors. And I would like to know the length of x plus y. Okay? What is this equal to? This is equal to, let me put the square here, x plus y transpose times x plus y, isn't it? Everybody is following? So what is this? Just if you take transpose of a summation, it is just goes inside, right? Now let me distribute these two parentheses. What do I have? X transpose times x, x transpose times y, plus y transpose times x, then y transpose times y, right? So this is a multiplication of vector. Yes? Why did I put square? Otherwise, I will put square root here, okay? As I did there. You don't have to, then you work with square root. So this is the square of the length, okay? Otherwise, you put a square root here. So we don't want to work with square roots. It doesn't make any difference. So what can you tell me about these? Are they equal or not? Equal, right? I said that there. These are scalars, right? You multiply a horizontal vector with a vertical vector, you get a scalar. If you take transpose of it, transpose of a scalar is just another scalar. So they are the same thing. So this is equal to y transpose x. So I can write here x transpose x plus y transpose y plus twice y transpose x. What is this? What is this? What was your name? Utku. What is this equal to? Definition? X transpose x is what? Abdul what is this? Length of x squared, right? And what is this? Okay. So plus 2y. When is the Pythagoras rule valid in multidimensional case? When does it become valid? When you look at this, so we have x plus y square is equal to x squared plus y squared plus twice y transpose x. So when would I have x plus y squared is equal to x squared plus y squared? When this is 0, right? So if y transpose x is equal to 0, then square of the hypotenuse, right, is equal to sum of the squares of the other two sides, right? Other two sides. So what are the two sides in n-dimensional case? We don't know, right? Okay. What do we call these vectors? These are called orthogonal, okay? If y transpose x equal to 0, then y is orthogonal to x. Y is orthogonal to X. Okay, this is very, very important and basic thing. So what we know in two-dimensional case generalizes to n-dimensional case. And again, the condition there is that X and Y are orthogonal. If they are orthogonal, then if you add those two vectors, you get a new vector, right? This is called X plus Y. This is X plus Y vector, right? Okay, which is V here. Okay, X plus Y vector. So the length of this square is equal to square of this orthogonal side plus square of this, the other orthogonal side. So in n-dimensional case, we just discovered that if you do this operation, what you get is that the same thing will hold true if and only if Y transpose X is equal to 0, which means Y is orthogonal to X. This could be a very simple exam question, right? Like the proofs I asked. Yes?
Can we explain the first equation?
This one? So I want to calculate the length of X plus Y. X is a vector in Rn. Y is a vector in Rn, right? X plus Y is another vector in Rn. So I want to calculate length of this in terms of length of X and Y. Okay? The definition of X plus Y length square is just, this is a vector transpose times itself, right? Like we did here. Okay? This is the definition. You just, it's not different thing.
Here you are adding the components square. Here
X plus Y is a vector, right? So I'm calculating the length of that vector. Okay? So call this, if you want, call this Z. Okay? So I want to calculate length of Z. So what is this? Z transpose Z, right? That's what this is. So I want to calculate the length of the vector X plus Y, which is Z. Did everybody understand this? Who did not understand it? Please, there is nothing to be ashamed of. Yes. Okay. If I give you a vector, let me just give you an example, okay? Let's say I have a vector V1 minus 1, 2. What is the length of V squared? What is this? Can you tell me? Just do it. It's here. Just let's do it. Okay. What is it going to be? Square of this plus square of this plus square of this, right? So we are adding up the squares of each component of. Okay, let's continue. 1 plus 1 plus 4. So it is 6. Okay? So let's say I have a vector x 1 minus 1, 1, and y is equal to 2, 1, 1. Okay? I want to know about the length of x plus y. So this is length of 1 minus 1, 1, 2, 1, 1. Okay? So I also want to know what is the length of x, what is length of y. Okay, what is the length of x? Okay, what is length of x? So it is 2 square plus 1 square plus 1 square. I'm sorry. It's the other one, right? 1 square plus minus 1 square plus 1 square. So it is 3. So what is, this is square. What is y square? That is, okay, Utku, what is y square? So it is 2 square plus 1 square plus 1 square. So it is 6. Okay, what is x plus y? That is equal to, let's add these, 3, 0, 2. So what is x plus y length square? That is equal to 3 square plus 0 square plus 2 square. So that is 9 plus 4, that is 13. So if x and y were orthogonal, what would we have? 13 would be equal to 6 plus 3, right? So it is not. So that means it's not orthogonal, right? So that's what we are doing here. So we said that so what is the length square of when you add two vectors, x plus y square? Length square is just x plus y transpose plus x plus y. Who agrees to this? Any question on this? Any question on this step? Yes?
I don't understand why it is true transpose of H.
Here it is. Okay? We said that okay. So okay, so V transpose V. So this is definition, okay? This is definition of length of a vector, okay? This is a definition. This is not the only way we define the norm. In general, we don't call them length. We call this norm of a vector, okay? This is the most used and easiest to handle norm of a vector, okay? So it is x1 square plus xn square. So this can be written as inner product of a vector by itself, which is equal to V transpose V. Do you agree to this one? This is definition. And that's equal to V transpose V, right?
Just multiply the two matrices.
Multiply the vector by itself. Multiply vector by itself. Okay? So how do you do that? This vector into this, x1 square plus x2 square plus xn square. That's what it is. Now, can I go back to this one now? Please do not use your phone during the lecture. Okay? Please listen. Okay? X plus y, I would like to know the length of x plus y. Okay? Similar to there, that means x plus y transpose plus times x plus y. You agree to this one now? Everybody agrees? Good. So this transpose, this is addition of two matrices, right? If vectors are also matrices, isn't it? Vector means just it's just one column, special case. N rows and one column. We call that a vector. So transpose, you just distribute it inside, and you have here two matrices, a summation of two matrices multiplied by summation of two other matrices, right? You just distribute this. X transpose X, X transpose Y, Y transpose X, Y transpose Y. Okay? So X transpose X, Y transpose Y, I just take them here. Then I said X transpose Y is equal to Y transpose X. Why is that true, Ibrahim? Abdul Fattah, why is that true? Because Y transpose X is a scalar, yes, thank you. It's a scalar number, right? When you multiply a matrix by itself, you get a scalar. So it is like, it's a scalar. Scalar transpose of 5 or 3.5 or -5 is just itself. Scalar is. Therefore, if you take transpose of this, it is X transpose Y. Okay, or Y transpose X. So they are the same thing. These two things are equal. Therefore, this is just equal to X transpose X, Y transpose Y plus twice Y transpose X. Okay. So when is the Pythagoras rule correct for this matrix? When is it valid? Okay, so said X plus Y squared, the length of the hypotenuse, is equal to the length of two sides, right? X and Y. When is that true? If Y transpose X is equal to 0. Okay? When Y transpose X becomes 0, then X plus Y length squared is equal to length of X squared plus length of Y squared. And these are very special pairs of vectors. So we don't call a vector orthogonal, right? By yourself, you cannot be orthogonal. So we talk about pairs of vectors being orthogonal with respect to each other, right? So therefore, if Y transpose X is equal to 0, then we say that's definition of orthogonality. Then we say X and Y are orthogonal vectors, or a pair of orthogonal vectors. Okay. Is this clear to everybody? If you didn't understand this, please ask again. Okay? Otherwise, you will not be able to follow the rest of the course. Not only class, but the rest of the course. This is very easy. Now everybody understood, right? Okay, good. So let me give you an orthogonal vector example. So this, since X plus Y square is not equal to, okay, cos Y, this is 13, and this is X was 3, and this was 6, right? So this is 9. So 13, 3, this is equal to 9. So this is 13 is different from 9, right? So therefore, X is not orthogonal to Y, okay? It is not orthogonal to Y. Let me give you another example. If X is, let's say, 1, -1, 0, Y is equal to 1, -1, 1, 0. Let's calculate Y transpose X. What's that? -1, 1, 0. This is 1, -1, 0. So what do we have? -1. This is, okay, let me make this orthogonal. -1 plus 1 and 0, right? So it is 0. So these two vectors are orthogonal. Is it clear? So if I give you two vectors and ask you, is this orthogonal, or when is it orthogonal? Can you answer that? Okay, for example, let's ask such a question. Let's say I have a vector X, 1, -1, and y is equal to 1 alpha. Okay, for what alpha? Values of alpha, y is orthogonal to x. Okay? Very simple question, isn't it? What should I do? Just multiply y transpose x. So that is 1 alpha into 1 minus 1, which is 1 minus alpha. So what should this be? Set this to equal to 0, right? If you set this equal to 0, so what should I have? Alpha should be equal to 1. If alpha is equal to 1, these two vectors are orthogonal, right? Good. Okay, now we will now start building upon this, okay? We will now say, if I have a vector A, okay, and I have another vector B, what is the projection of B into A? Meaning, can I write B into two components such that one component is in the same direction as A, and I have another component that's perpendicular to that, and these two add together to get B. So let's call this vector P, okay? And what would this be? This would be B minus P, right? So if you add these two together, P and B minus P, you get what? This is called error. Let's call this error. So if I decompose B as such, I find a vector P and another vector B minus P such that P and B minus P are orthogonal, okay? In words, P and B minus P are orthogonal. Gece uyumadın mı kız? Bugün imtihan mı vardı sizin? İmtihanınız var mıydı? Çok çok önemli bunlar. Git yüzünü yıka gel istersen. Okay? So I want to project, so this P is called the projection of B into A. Okay? So how do we do this in two dimensions? Remember? We say that if the angle is theta, how do you find this length of this P? Yeah, so it is B, length of B multiplied by cosine theta will give you P, right? So we know that in two dimensions, how to do that. But here we are not going to talk about these things. It's not necessary. We will do it in much better ways, okay? So you are familiar with this. So we are talking about now projection of a vector into another vector. Okay? So here we have, of course, this P is what? P is vector A multiplied by some x that we don't know, right? If this x is too small, it's going to be like this, so it's not going to be 90 degrees, right? If it is too large, then it's going to be like this, so it's going to be less than 90 degrees. So we have to find the right x so that this becomes perpendicular, right? We have to find the x which will make sure that this partition of B into P and B minus P is just right, okay? So what is the condition for that? So we want P and B minus P be perpendicular. So how do we check that? How do we do that? What is the perpendicular condition? Orthogonality. So what does it mean? Of course, if this error is perpendicular to P, it is also perpendicular to A, isn't it? So what can I say then? What should I have? Their inner product multiplication is 0. Good. So I have to have A transpose times B minus P should be 0, right? That is the orthogonality condition. If this is satisfied, then this will be perpendicular to this one, okay? Okay? So what was this P? A transpose times B minus, this was AX, isn't it? We are trying to find what X is, isn't it? So just distribute this again. A transpose B minus A transpose A. I'm writing this with arrows so that you don't confuse scalars, and this is also B, right? Equal to 0. So you have, take this to the other side, you have A transpose A times X is equal to A transpose B. In other words, X is equal to A transpose B over A transpose A. Right? This is X. We will do example as well. Okay? So this is the most beautiful condition, okay? No need to try to find the angle and multiply with the cosine and this and that. No need, right? This is the beauty of linear algebra. We have the orthogonality condition. If that is satisfied, so this vector has to be orthogonal to this vector. Therefore, inner product of A with this error has to be 0. And that gives you the solution. No cosines, no nothing. Of course, cosine is hidden there, but you don't need to call it cosine. So what is P, projection vector? This is equal to A transpose B. This is X, so what do I have here? Multiplied by A. Okay. This is a scalar, so therefore I can just write it like this. A transpose over A transpose A times B. Okay? So this is the projection. We will now do example. We also call this projection matrix, it's called A transpose divided by A transpose A. So if you multiply this with B, you get projection of B into A, subspace A, right? A is a subspace, one-dimensional subspace of Rn. If you multiply with C, what do you get? Projection of C into A. So this is the projection matrix, right? Let me do an example for this. Okay, example. So let's say A is 1, 1, 1. B is 2, minus 1, 3. Okay? I want to calculate projection of, please find projection of B into A. subspace of A, okay? This is part 1. Part 2, find projection of A into B, okay? Let's see what is the difference. Who would like to do this? Can somebody do it for me? Okay, I will do this, then you do later. So I have now an A again, right? I have a B. It's very important to understand this. B, I want to find this here, right? This is P. I want to find the projection vector P. So what we just discovered very easily is that P is, if you are projecting something onto A, P is just A transpose B over A transpose A times A. So what is A transpose B? So it is 1, 1, 1 into 2 minus 1, 3. So what is this? 2 minus 1 becomes 1 plus 3 is 4, right? And what is A transpose A? A transpose A is just 1, 1, 1 into 1, 1, 1, right? So it is 3. So then this is equal to 4 over 3 times 1, 1, 1. Okay? So what did I find? How do I check if I want to check? How do I check what I did is true? I would calculate E, isn't it? So E is B minus P. What is that? B is 2 minus 1, 3 minus 4 over 3 times 1, 1, 1. And that is 2 minus 4 over 3 minus 1 minus 4 over 3, 3 minus 4 over 3. That gives you 2 over 3 minus 7 over 3 minus 5 over 3, right? So what should I have? This E should be perpendicular to A, right? Is it true? So that means A transpose E should be 0, is it? A transpose 1, 1, 1 times 2 over 3 minus 7 over 3, 5 over 3. Is it 0? Yes, right? 2 over 3 plus minus 7 over 3 plus 5 over 3 is 0. So they are perpendicular. So therefore, we found the orthogonal decomposition of vector B with respect to A, isn't it? We found the projection of B into A, right? So projection of B into A is just 4 over 3 times A, okay? And the remaining part, which is error, B minus P, is this, and this is perpendicular to A. Therefore, so what is the remaining part? Now, part B is what? Let me do the now other half. So I want to find now, so this was what we had, A and B. Now what do I want to find? I want to find projection of A into B, okay? So what does that mean? I want to find this. So let me call this P1. I want to now find projection of A into B. So it is a different problem, isn't it? Okay? So what is that? So what would that be? P1 is equal to what? Just take the same thing, right? B transpose A over B transpose B into B. So what is B transpose A? B transpose is just 2 minus 1, 3. A is 1, 1, 1. Of course, B transpose A is equal to A transpose B. It's the same thing. So it is 2 minus 1 plus 3. So it is 4. B transpose B is equal to, what is it, Ibrahim? 4 plus 1 plus 9. So it is 13. 14. Okay. Did we make a mistake there? No, we didn't calculate it. Okay. 14. So what is P1 in that case? P1 is equal to 4 over 14 times B. B is 2 minus 1 and 3. Okay? So this is the projection of, this is the projection of A into B, right? Of course, they are different. They are different. This, why are they? Why should they be different? Because this is the direction of B, right? So we are looking into the portion of orthogonal component in A that is in the same direction as B. In the other one, we were looking for the orthogonal component of B in the same direction of A. Just to verify, let's calculate the error, right? Error is equal to A minus P1 in this case, isn't it? This is A minus P1. So if you add these two together, you get this vector plus this vector gives you this vector, right? So this is A is 1, 1, 1, minus P1 is 4 over 14 is just 2 over 7. So 2 over 7 times 2 minus 1, 3, which would be 1 minus 4 over 7, 1 plus 2 over 7, 1 minus 6 over 7. And that makes 3 over 7, 9 over 7, 1 over 7. So what should we have? What should we have now? What do we expect? Inner product, not multiplication. Inner product of E, so B, let's call it B transpose E, which is of course E transpose B, right? Should be 0. Is it 0? Okay? If we didn't make a mistake, this should be satisfied. Let's see. B transpose is what? 2 minus 1, 3 into 3 over 7, 9 over 7, and 1 over 7. And this gives you 6 over 7, right? This is 9 over 7, and this gives you 3 over 7. So is it true? Yes. So you should now, at this point, you should very clearly know how to find projection of one vector into another one. If I were to ask you, find the orthogonal components of A with respect to B, what would you tell me? You would tell me, sir, orthogonal components are this. I can write B is equal to, in the first case, okay, P plus B minus P, and here P and B minus P are orthogonal, right? Of course, we didn't check this. What did we check? We checked A and B plus B are orthogonal, right? Why? Because they are in the same direction, okay? Let's do that as well, okay? Afterwards, if it is true or not. And in the second case, you will tell me, okay, So this is A is equal to P1 plus A minus P1. Then this is P1 and A minus P1 are orthogonal. So therefore, you found an orthogonal decomposition of B. You wrote it in two components that are orthogonal to each other. This is very important, okay? Let's see if this is true. Let's just do it for this one, okay? What was P1? P1 is here. So P1 is this. So P1 transpose times E. What is this? 4 over 14 times 2 minus 1, 3. 2 minus 1, 3 into E. What is E? So 3 over 7, 9 over 7, 1 over 7, right? Of course it is, because it's just this, whatever you multiply here doesn't matter. This into this gives you 0. So that is 6 over 7 minus 9 over 7 plus 3 over 7 times 4 over 14, which is equal to 0. Because A, so in this case, B and P1 are in the same direction. In the first case, A and P are in the same direction. Okay? So therefore, they are orthogonal. So we talk about A and B being orthogonal to each other, but projection of A into B is not same as projection of B into A. So don't get confused. Let's just give a 5 minutes break. Or should I just continue without break? Let's continue without break. Okay? So that we can leave you earlier. We can leave earlier. Okay? Okay. So this is how you obtain projection of a vector. Another very important thing I want to tell you is this. We talk about orthogonal subspaces. Okay? Orthogonal subspaces. Let's say we have Rn, okay? So we are in n-dimensional real vector space. And in this one, we have V and W are subspaces of Rn. Like example, in Rn, if I have the matrix M by N matrix, can you tell me two subspaces? For example, I have column space of A. What was the dimension of this? This was subspace of what? So the vectors in this column space of A, what are their dimensions? N, right? So this is a subspace of Rn. And what was the dimension of this? So we had lots of this in the midterm exam, right? Dimension of this is R, right? So what is another subspace in Rn? What is another subspace in Rn? Has vectors that has n components. What are they? It is the null space of A transpose, right? Null space of this is wait a minute. This column, these A's, how many components do they have? I said m minus n. Each column, this is m, right? This is m. So you have this matrix has m rows and n columns. Therefore, the vectors in these columns of this has m components. Therefore, this column space of A is a subspace of Rm, right? And it is dimension of the subspace is R, meaning we have R linearly independent columns of A. That's what it means. Okay? What is another subspace that is a subspace of Rm? What is that? It is the left null space of A, isn't it? Or in other words, it is the null space of A transpose, right? What is the dimension of this? Dimension of left null space of A is M minus R. And the other ones were column space of A transpose is a subspace of Rn, right? And null space of A, how many components does it have? It's just X multiplying this, it has N, right? So therefore this is, so you cannot memorize this. You cannot handle these things by memory. You have to understand it. If you understand it, it's very easy, right? And dimension of column space of A, column space of A transpose here, A transpose. A transpose is R, and null space of dimension of null space of A is N minus R. Okay? Now, so think of this V and W as two subspaces of Rn. They don't have to be related to an A, but these are just two subspaces like these ones. It is CA transpose and A pairs, right? Two subspaces, CA and NA transpose. We say that, let me write it here. So orthogonal subspaces if for every little v in V and W in W, okay? So this is name of the subspace. This is a vector in that subspace, right? This is name of the subspace is capital W, and the little w is just a member of that subspace. So if for every you have V dot product W equal to 0, then these two subspaces are, okay, orthogonal. Orthogonal. Okay? V and W are orthogonal, means okay? So we talk about, can you give me examples of this? I just wrote this here, okay? For example, let's talk about this one. Let's talk about this one, okay? I have C1, Cn. This is my A matrix, right? And I have here X equal to 0. What are these X's? The X's that satisfy this, we call them what? Left null space of, they span the left null space of A, right? And so what can you tell me about this? This X, inner product C1 is equal to 0, isn't it? And then X inner product C2, that's also equal to 0. X inner product Cn is equal to 0. So this, let me call it X transpose, okay, X transpose. So the inner product. X transpose into this is 0. X transpose into this is 0. So this was 0, 0, 0, right? This is a 0, 0 vector. So this is a matrix. I now look into this as terms of columns. So that means, what does this mean? Excuse me? Orthogonal to column space. So these two subspaces are orthogonal. Okay? Very good. What was your name? Jakub. Jakub got 100, by the way. Congratulations. Okay? So this means X transpose C1 equal to 0. That means for every X that satisfies this, all those X's, they span the left null space of A, right? And on the other hand, they are orthogonal to every column of this. And these columns, they span the column space of A, right? Just give me any linear combination of this, not only each one of them, but take any linear combination of this, right? If I take, for example, alpha 1 C1, alpha 2 C2, alpha n Cn. So this is, let's call this a vector y, okay? So I just took just any linear combinations of these columns of A. I obtained a new vector. Where is this vector, by the way? This vector belongs to what? Jakub, this belongs to where? I took linear combination of the columns of A. So the vector I obtained is in which subspace? Column space of A, right? That's the definition of it. So therefore, if I multiply this X transpose times y, what will this be? Alpha 1 times X transpose C1 plus alpha 2 times X transpose C2 dot alpha n times X transpose Cn. So this is 0. This is 0. All of these are, therefore, they add up to 0, right? So therefore, if you find all of the x's that span the left null space of A, you will see that every one of those vectors are orthogonal to all the columns of A. Therefore, they are orthogonal to column space of A. Okay? So therefore, we say that now we know something new here. We say that column space of A is orthogonal to null space of A transpose, or left null space of A. Okay? Okay, let's now have a look at this one. So what am I going to do about the other null space? How do I look at it? Do I look at it as columns or rows? Rows, right? So let's take now A, X. So this is row 1, row 2, row n into X, right? X equal to 0. What does this mean? These x's, they span, these x's, they form what? These are null space of, so the set of x's, the set of x's form the null space of A, right? So what do we have? R1 transpose, R1, so these are row vectors. Therefore, R1 times X is equal to 0, R2 times X is equal to 0, right? Etc. Rn times X is equal to 0. If I take the transpose of this, what do I have? X transpose into A transpose equal to 0, right? So these are really, so what you have here is that column space of A transpose is orthogonal to null space of A. Okay? So these are two orthogonal, so that's why it was very important to understand the four fundamental subspaces. These are These have very beautiful properties. They are orthogonal to each other, okay, in pairs. Of course, one of them is m-dimensional, subspace of m-dimensional real vector space. The other one is subspace of n-dimensional real vector space, okay? Now, we notice, so let's okay, doing an example on this will take a lot of time. You just check this in the exam, okay? The question you solve in the exam, verify that as a homework question, verify that this is satisfied, meaning, it's of course, by definition they are orthogonal, right? You don't need to verify it even. It's just orthogonal. Okay, now I want to see, now this was projection of a vector into another vector. How about projection of a vector into a subspace? Of course, this was also a subspace, isn't it? When you talk about projection of a vector into another vector, that means projection of vector into a very special subspace. What is that subspace, dimension of that subspace? Abdul Fattah, what is the dimension of that subspace? 1, right? What if the projection you are doing is not one-dimensional, right? It is, if it is just any subspace, right? So I have, let's say, projection. So that was projection of a vector into another vector, right? Projection of a vector to a vector. Now projection of a vector, projection of a vector into a subspace. So I have, let's say, a subspace, okay? I have a vector B. I want to calculate the orthogonal projection of this B into the subspace. Of course, this subspace is just obtained by taking linear combination of columns of a matrix A, okay? So this subspace is defined as the linear combination of the columns of a matrix A. Okay? So any y in this, let's call this subspace V, let's say, in V is obtained as y is equal to AX. Okay? Just taking all possible linear combinations of the columns of A, you obtain y is equal to AX, will give you a vector in this one. So we are given a vector B, okay, that's not necessarily in this subspace. What does that mean in terms of subspaces? So if I give you a B, I tell you that this is not necessarily an element of V, okay? That's not in V. Meaning, this B cannot be obtained as a linear combination of the columns of A. That's what it means, right? So you have this, in other words, it's like this. You have an equation AX is equal to B, okay? You have an equation AX equal to B. Let me give you an example. Let's say 1, -1, 3, 4, 5, 6, and 0. 1, 1, 3, 1, -1, 1, 1, okay? You have x1, x2, and you have here what? 1, 3, -1, 1, 0, 5, okay? You have an A, that columns of it gives you a subspace, okay? And you have a B, okay? Can this equation be solved? Can you solve this equation? Sometimes yes, sometimes no, right? When can I solve it? If B belongs to the subspace of A, CA, right? Column space. So if B is in the column space of A, then this equation has a solution, right? Meaning B is a linear combination of, isn't it? This is x1 times first column plus x2 times the second column, isn't it? It's very important to look at it this way, right? x1 times the first column plus x2 times the second column should give you this column. So it is a linear combination of the columns. So if B is not a member of the column space of A, then there is no such x1 and x2, right? So in that case, what do we want to do? We want to see, can I find an orthogonal projection of B into this subspace? Okay, this is the question we are asking, right? Okay. So this is very interesting. This will wake you up. Okay. So this P will be what? Since it is in this subspace, how can I write it? P is equal to linear combination of the columns of A, right? Let me call it X. Of course, X in the first case was a scalar that we were trying to find out. Now this is a vector. Okay, so the question is, find a vector such that A times that vector, okay, gives you a P, and this P should be what? It should be, it is of course, for any X, A times X is in the subspace, right? Is in column space of A, for any X. So which one are we looking for? We are looking for, okay, that is
perpendicular to the
exactly the error, right? That we are looking for this AX such that the error vector, error is what? B minus P, right? Which is B minus AX. Should be perpendicular to what?
the difference between
It will be what? So it will be, this E will be perpendicular to every vector in A, column space of A, right? So every vector in A will be perpendicular to this one, right? So can I say the following in that case? Like we did there, right? This one. We explained it here. So can I say the following? It will be B minus AX transpose, of course. So we have to make this inner product. This will be perpendicular to the first column of A, right? It will be perpendicular to second column of A, right? It has to be perpendicular to all vectors in column space of A, isn't it? That's what it means. So it will be perpendicular to, how many columns do I have? N. So it will be perpendicular to all of them, right? In other words, can I write them like this? Let me go to that. So I can put this all together, right? I have to have B minus AX transpose times C1, C2, Cn is equal to 0, right? 0 vector. What is this? This is A. let me take transpose of this. What is this going to be? A transpose times B minus AX equal to 0. So what is this? What does it tell you about? What is B minus AX is what? In left null space of A, right? So B minus AX has to be the left null space of A, which is null space of A transpose, right? Isn't this beautiful? When you understand the subspaces, everything becomes very nicely, they becomes clear and they fall into place. So the rest is just child play, right? From here, this is just an interpretation, but we didn't have to call it even this null space or that null space, but this is what it means. So this is what? A transpose B is equal to A transpose AX. In other words, X is equal to A transpose A inverse times A transpose B. So this vector, of course, in the first case, when we had projection of a vector into another vector, X was a scalar, right? Now it is a vector. It's another vector. It's a vector that is determined like that. Okay? So what is P in that case? P was what? AX, right? This is how we defined it. It's just we are looking for the right combination of the columns of A that will make it perpendicular to this B, to B. Okay, so the projection of B will be perpendicular to the error. Okay, so that's equal to A transpose A inverse A transpose B. Okay, so this matrix has a special name. This is called the projection matrix. Let me ask you a simple question, just intuition. Let's say I projected this B. So this is telling me that if somebody gives you a B, okay, and you want to project into A, it is independent of B. You just find this projection matrix, and whatever matrix they want to project into this subspace, just multiply it with this matrix. It is independent. As you see, this projection matrix is independent of B. Okay? It just depends on the columns of the subspace. What it's telling us that find this projection matrix for that subspace and just multiply it with the vector you want to project. That's going to give you the orthogonal projection of it. Okay? That's so beautiful, isn't it? Okay, let's say I started with a B and obtained the projection of that vector into my subspace. If I take that projection and project it again, what do I get? I projected B into my subspace, column space of A, right? And I obtain a P. If I project it again, what do I get? I get the same thing, right? It doesn't change. So what does that mean? That means this matrix, so I took a B, projected it, and so multiplied with this P, with capital P, okay? I obtain my projection vector P, right? So if I want to multiply this, if I want to project this P again, what should I get? If if all we did makes any sense, this should give me P. Why? Why is that? Because P is in column space of A, right? That was the condition. P, the projected, the part of B, okay, was P. What was that? It was the orthogonal projection of vector B into the column space of A, right? So it is a part of column space of A. So projection of it is just 100%. All of it will come back. So you will recover it. So that would mean P times B. So that is P square B. So this should be identity, right? Let's see if it is true. P times P is what? A transpose A inverse, A transpose. This is P. Let's write this again. A transpose A inverse, A transpose. So is this does it give you, I'm sure this should be P. P squared is equal to P. So what does this give you? You just look at this one, and this gives you what? Identity. What remains is A transpose A inverse, A transpose, right? So it is equal to P. Therefore, P squared is equal to P. Okay, let's say given B is equal to 1, minus 1, 1, and a subspace V is given as the column space of A is equal to 1, 2, 0, 1, 1, 0. Okay? Find the orthogonal projection of B into V. Okay? Is this question clear? Utku, is it clear? What am I asking here? So I defined a subspace, isn't it? I said, so in this topic, we need a subspace. So you need to give definition of a subspace. In this case, I gave it as a column space of this matrix A. I could give it in a more tricky way, right? I could tell you I have x1, x2, x3, x4, and this x1 and x2 has this kind of relationship. So they define a subspace, right? I give you another vector and I ask you find the projection of that vector into this. So what am I trying to find out? I'm trying to find out whether you really understood what you are doing or did you just memorize. Okay? So it's very important to understand what is a vector space, what is subspace, and all those. Okay. So I gave you a subspace, and I gave you a vector. I did not calculate it beforehand. It's most probably, right? It would be very surprising if this was a member of this subspace, right? So I'm asking you to find projection of this vector into the subspace defined as such. Is it clear? So, as I said, as we develop there, we need to find the projection matrix. P is equal to A transpose A inverse times A transpose. So let's calculate A transpose A. So what is A transpose A? A transpose is 1, 2, 0, 1, 1, 0, 1, 2, 0, 1, 1, 0. So this is 5, and this is 3, and this is 3, and this is 4. So what is inverse of A transpose A? That's going to be, so this is 20 minus 9, so 11. You interchange these ones, and you change the sign of these. So this is very good. It's 1. So the determinant is 1. So thank you. Okay? Okay. So let's continue. A transpose A inverse times A transpose is 2 minus 3 minus 3, 5 times A transpose is 1, 2, 0, 1, 1, 0. So it's going to be 2 minus 3 is minus 1, 4 minus 3 is 1, and this is 0. Minus 3 plus 5 is 2. Minus 6 plus 5 is minus 1. Minus 6 plus, yes. And this is 0. Did I do it right? Please check. Then I have A transpose A inverse times A transpose is equal to 1, 2, 0, 1, 1, 0 times minus 1, 1, 0, 2, minus 1, 0. Right? That's going to give you 1, 0, 0, 0. This is minus 2. Huh? What 1? Huh. This is yes. 2 minus 1 is 1, and this is 0, 0, 0, 0. So you have an identity here. Okay? So this is the projection matrix. So what is projection of B into A? It's just projection matrix times B, right? Just any vector you give me. So it's going to be 1, 0, 0, 0, 1, 0, 0, 0, 0 times B was what? 1 minus 1 and 1. So 1 minus 1 and 0. That's it. So how do I check that did I make a mistake or anything? How can I make sure? Huh? Just now, how can I make sure? The error, right? Find the error vector. So just to check, okay? Error vector is B minus P, which is B was 1 minus 1, 1, and this is 1 minus 1, 0. So what is the error vector? 0, 0, 1. Okay? So E transpose times A. So 0, 0, 1 into, what was A again? 1, 2, 0, 1, 1, 0. Is this equal to 0? It is, right? It is. So what we did is right. Meaning, we were able to obtain orthogonal projection of this vector B into A. If I give you another C, let's say, 3, 5, 6, how do I find the orthogonal projection? Projection matrix doesn't change. You just, once you obtain this projection matrix, you just multiply it with C at this time, right? So it is not going to change anything. Who understood this? Who did not understand it? Okay. Who else? Please, I'm sure there are more people who didn't understand. Just one? You came late. Okay. If you came late, it will be difficult to review. You watch the video, and if you have any more questions, ask us. Okay? Yes? Oh. You see, this is P. This is the P, right? So you just A transpose A and A transpose A inverse. A transpose A inverse. So you just consider this as one unit, and you have A transpose inverse here. So they make identity, isn't it?
So A transpose times A gives a matrix.
Yes.
A transpose times A inverse gives the inverse of that matrix.
A transpose A inverse, right?
Gives the inverse of
Inverse of that, of course. That's the definition of it. When you have A transpose A here, and you have A transpose A inverse, this is inverse of that. That's the definition of that. Okay? That's what it means. So if you write something, if you write X times X inverse, that means the definition is that you call this if this is satisfied. That's the definition of it. If this is so, then you can call this A transpose A inverse, okay? That's the definition of matrix inverse. Okay. This is clear? What are you asking? Ask me.
Asking about the projection of the thing with A transpose and inverse. I was asking if when we use it.
When we use it. When you use this P, you mean? Are you asking about this P matrix?
Yes.
So this P matrix is the projection matrix. Meaning if I give you a subspace, this subspace, every subspace has a projection matrix. Meaning it's like if you have another vector, if you have any vector, multiplying with this P will tell you what is the orthogonal component of that vector in this subspace. Okay? This is what it does. What is, by the way, the remaining one? What is the error vector? Okay? Error vector is also important, right? It is the vector that is orthogonal to this subspace. What is that? Yeah, this is projection matrix. What? This is little p. This is capital P. Okay? These are not the same P. That's why I underline this here. This is, we found what? Did you take care of it? It's clarified now? Okay, good. I didn't understand what was the problem, but anyway. So we have a subspace V, okay, is column space of A, okay, is defined as column space of A. Okay, and we are given a B. So what we found out is that given a B is projected into CA, and this is done with P is equal to, this is the projection of B. It's very difficult for Arabs, right? B and P, it's a big problem. Into column space of A. Okay? So this is A transpose A inverse A transpose times B. Okay? So this is the projection matrix. So what is the other component? So B is equal to, now P plus what? B minus A. So this is like, we have a subspace, okay? This is like you have an A and you have a B. So this B, you remember we found these two components, okay? And this was error. So we wrote this B as P plus E, right? It's the same thing. B is equal to P, right? These are orthogonal components. Okay? So what can I say here? For example, what can I say? In terms of the length, Pythagoras rule, what will it tell me? B norm square is equal to P square, because these are orthogonal, isn't it? So how can I find this in terms of this projection vector? B minus P would be equal to what? B minus A transpose A inverse A transpose times B. In other words, if you take common, it's I minus A transpose A inverse A transpose times B, okay? So this will give you the orthogonal projection of B into the subspace A, and this will give you the orthogonal component of that, okay? We will use this in Gram-Schmidt orthogonalization process, okay? We will talk about that in next class. So we have another thing to do today. I'm not going to start that, I will do it next week. But this tells you this is a way, so orthogonal projection of a vector into subspace is not more valuable than the other part, okay? It's not a matter of which one is better or worse. It's just to identify what is what. So this is the orthogonal component with respect to A. So you can look at this like, this is, you have column space of A, this is what? Null space of A transpose, right? So this belongs to null space of A transpose. So this is like to dissect your vector into different portions, okay? So in Gram-Schmidt orthogonalization process, we will tell you that when you are given a set of vectors, let's say x1, x2, xn, n vectors, and you would like to find a set of orthogonal vectors or orthonormal vectors that span the same subspace and they are orthogonal to each other, right? So how to do that? This is exactly how we are going to do it. So after you understand all these things, the rest is just child play, okay? So it's very important to be able to understand what is a norm, what is orthogonality and projection and complement of the projection. If you understand these things, the rest of this class is all built on these things. Of course, these are based on what we did so far in the course. So therefore, it's going to be easy sailing if you understood all these. Okay. Now, I talked about this example here. I want to go back to this one, okay? So what did we find out? We found out that, okay, we don't know, there is no solution for this, but we found an orthogonal projection of B into A. And so we could not find an X, so we cannot, in general, find an X that will exactly satisfy this equation, right? So what we did is, so far we said, okay, can we find projection of B into the column space of A? So we found an X hat that generates P, the orthogonal B into CA, okay? So how good is this one, okay? The question is, okay, you did, so math is nice and everything, but how good is it? So we cannot satisfy this. What should we look for? By the way, how do we face these problems? This is very common in engineering and science. As engineers and scientists, we do measurements, okay? We measure the space, we measure the material, we measure light, we measure electricity. We measure, observe, collect data on anything, okay? Zillions of data. And from that data, we try to learn. We learn from the data and try to identify the physical process and then improve upon it, okay? So you talk about electrical engineering, mechanical engineering, civil engineering, astronomy, chemistry, anything you think about, you will always face this problem. You will do lots of observation, and you will try to identify a few parameters. In this case, we did how many observations? 1, 2, 3, 4, 5, 6, 7 observations, and we obtained this data, right? For such and such parameter, you have this. And we are trying to find we are trying to identify x1 and x2. But it turns out that such an equation doesn't have a solution. What would be a silly way of taking care of this? When would I have a guaranteed solution? No, that's no solution. I'm talking about exact solution. Okay? This doesn't have a solution, right? I can say that you can tell me, doctor, are you crazy? You want to identify two parameters? Just make two measurements. Then you have two equations and two unknowns, and you have the results. Why do you make trouble yourself and have so many equations and you don't know what to do about it, right? Does this make sense? Is this intuitive? Just so that I don't know how to solve this equation, I just do a few observations and try to, so that my equation has two equations and two unknowns? Of course it doesn't. What is the principle? You would think that the more observation you make, the more data you have, the more you learn, right? You learn more about your process. So more observations would mean better results, better results, better results. Therefore, we should find a way to make use of the data we collected. Okay, what would you suggest? What would be a good way? So can I look at this like, can I look at this as error is equal to AX minus B, meaning I have E1, E2, En. I have here 1, minus 1, 3, 4, 5, 6, 0. And I have here 1, 1, 3, minus 1, 1, 1 times x1, x2 minus 1, 3, minus 1, 1, 0, 5. Okay? Ideally, what would I desire? I would desire that E1 should be 0. Right? I would be able to find x1 and x2 such that E1 is 0, E2 is 0, En is 0. If this is not possible, when is that possible again? I will repeat it. When is that possible? If this vector is in the column space of this matrix, right? And most likely it's not going to be in that matrix, in that column space. In that case, what is the next best thing you can do? Please tell me. What is the best you can do? If you cannot make it 0, then what can you do? Minimize it. Who said that? Thank you. What's your name? Mustafa. Great. You minimize it. Minimize it in the sense of what? So you have to measure it, right? So what is the minimum I can make, right? So look at this vector, okay? This, let's call this vector E. And this is a parameter of what? X1 and X2, right? So you just calculate the norm square of this and minimize this. Okay, so you try to minimize this. So in general, let me continue here. Did you learn, everybody did learn about derivatives? Is there anybody in this class who never heard about derivative? Turev. You are not taking calculus 1 now? Nasıl muafsın? Bir yerde aldın yani. Türevi biliyorsun demek o. Okay, find out. Okay. Okay. And did you, of course, in the calculus course, you are taking this term. Even if you didn't learn anything in high school, you should know about derivative and maximum and minimum of a function, right? Everybody, if the calculus course, we are now at what, 8th week since the beginning? In the 8th week, you should by now, we should finish maximums and minimums and everything. So therefore, everybody knows about that. Okay. Okay, so we have, in general, we have Ax is equal to B, where A is m by n, and B is just m by 1, okay? And you would like to find a solution of this, where in most cases, m could be much larger than n. So you could have just few unknowns, but too many equations, okay, which would mean there is no solution. Okay? So in that case, the next best thing to do is to make E is equal to AX minus B as small as possible. Okay? This is what you would do. So, of course, we talked about the length of E, right? Length of E, when you have E, which is E transpose E. This was E1 square, E2 square, En square. This is how we measure it, and this is the easiest way and very easy to handle, and it has to do with the energy of something. If this was a signal, a digital signal, we call this the energy of the signal in electrical engineering. In many other things, always the sum of the squares or integral of the square of a signal or integral of a square of function would mean the energy of, is related to the energy of that signal, okay? So it has a physical meaning. But this is not the only thing only way we talk about length of vectors. In general, we call them norm of a vector, okay? So we call them normed vector spaces. We'll talk about this in your third and fourth year in school in some courses or in graduate school. So another length of or norm of a vector would be what? You would like to have, when you have a vector, I'm not going to talk too much about it, but just so that you hear about it, because some of you will be like crazy about mathematics like me, so you would wonder what else, okay? You would talk about, for example, you would say infinity norm of E is equal to maximum of EI. Say that I just look at the worst case, okay? The error for me is the largest deviation. That's what is important for me, okay? So you are talking about minimizing the sum of the squares. I don't care about that. I would like to have the maximum of this minimum, okay? So all of them should be as small as possible, okay? So my PhD work was on that, okay? So how to minimize the maximum. Okay, now we'll talk about, of course, this one. This is very easy to do. There are other ones. For example, another one that since I wrote, let me write a few more of them. Okay. Another one is, this is called one norm. Okay, and this is E1 plus E2 plus En, or P norm is called for example, for any P. Okay? So you have any P greater than 1. So you have many different ways of measuring vectors. But the most common one is the one we are talking about everywhere. Why? The main reason is it is very easy to handle, okay? Very, very easy to handle. It's the easiest to handle. And a second reason, also it makes sense. So just small reminder. Okay? If you have a function f of x, okay? It's from calculus. These points are called what? Let's say x1, x2, x3. This is x. This is y, and this is the function f of x. What do we call these points? Extremum points, right? This is where the function is either has a local minimum or local maximum. What does that mean in terms of derivative of the function? Ibrahim, what does that mean? Derivative is equal to 0. Beautiful. Yes. So derivative at these points, okay, f prime x is equal to 0. Okay? In multidimensional case, so this is single variable. In multidimensional case, in multivariable case, if you have f of x1, x2, xn, again, you have minimums and maximums. Of course, we cannot plot them, right? Because it is a multidimensional space, so we cannot visualize it, but we can talk about maximums and minimums. So what do we have? Maximums and minimums satisfy what? The f, these are partial derivatives. Did you hear about partial derivatives? Who did not hear about partial derivatives? You are the only one who didn't? Did you hear about partial derivatives? Kısmi türev. So I have to translate. Okay? So all the points that satisfy this condition, this is a necessary condition for extremum points, okay? Minimum or maximum has to satisfy this. But it does not always mean that it's a maximum or minimum. You can have other very interesting cases, like saddle points. Like in one direction, it is a maximum. In the other direction, it's a minimum, okay? Or you can have a turning point. It comes like in x cubed, it comes, it makes 0, and then goes again. It's not necessarily a maximum or a minimum or a saddle point. So you have many, but in our case, we will not face those funny problems, okay? So a necessary condition for optimum is that we have these derivatives equal to 0. Now, what I will do is I will just apply this to our problem here, okay? I will just apply this multivariable case. We have more than one x, x1, x2, xn that we want to solve. And we have an error function, we want to minimize it. So easy, right? Let's just do that. You will see the relationship with the projection. That's why we are doing this. So you will find out that indeed the solution we obtain by projection is the optimal solution for that system of linear equation. Okay, that's what I want to prove to you now. So E is equal to B minus AX. Okay. E norm square is B minus AX transpose B minus AX. Okay. So you multiply this out. What do we get? Okay, let me just B transpose minus AX transpose A transpose B minus AX. Okay, so what do I have? Jakub, what do I have here? B transpose B. These are all scalar, right? B transpose B is a scalar, isn't it? So it is, okay, then B transpose AX, then X transpose A transpose B. What else? X transpose A transpose A X. What can you tell me about these? What is the transpose of this? X transpose A transpose B. Is it same as this one? Why? Ibrahim, why? What is this? Is it a matrix or a vector or a scalar? It's a scalar, right? Transpose of it is equal to itself. So this is a vector. This is a horizontal vector. And this is a vertical vector. You will multiply, then we get a number. So transpose of it is equal to itself. Therefore, this is equal to X transpose A transpose AX minus 2X transpose A transpose B plus B transpose B, right? So this is, I want to minimize E. The minimums of E, are they the same as minimum of E square? If something minimizes E, do you think it also minimizes E square? Of course it does, right? Same, they are minimum at the same point. Of course, their value is not the same. Their value is just square of the other one. So if I look at this like f, x1, x2, xn. So this is a function of n variables. Where are those? These x's is just x1, x2, xn, right? So I need df1, dx1, okay? So what I will do is I will just write this in an open form so that we can see that, right? So I will just, this is x1, x2, xn, A transpose A, x1, x2, xn. So if I take derivative of this, let's take derivative of this with respect to x. What is it going to be? So I have multiplication of two functions here, right? So derivative of this multiplied by this, chain rule, right? And then this times derivative of, plus this times derivative of that, right? So this is equal to, what is derivative of the respect to x1? What is it? 1. This? 0, right? Partial derivative. So partial derivative of x2 with respect to x1 is 0. So partial derivative of x1 is 1, okay? Then this is A transpose A, and this is x1 plus. Now the other part, this remains the same, right? x1, xn, A transpose A, and what is this going to be? Excellent. Okay? So I will do this for all of them, right? What do I get? So I have df1 dx1 is 1, 0, 0, A transpose A, x1, xn, plus x1, xn, A transpose A, 1, 0, 0, 0. Let's look at the other one. What is the derivative of this one? What is this going to be? Somebody tell me. 1, 0, 0, right? So minus 2 times 1, 0, 0, 0, and that is A transpose B. And what is the derivative of that one? 0. Very good. Okay? df dx2 will be what? Abdul Fattah, what is it going to be? What is derivative with respect to x2? 0, 1. Okay. And this is going to be, and this is 0, 1, right? And minus 2 times 0, 1, etc. And I continue like that. df dxn will be 0, 0, 0, 1, A transpose A, x1, xn, right? x1, xn, A transpose A, 0, 0, 0, 1, minus twice. Okay. So this is equal to 0, that is equal to 0, okay? So how can I put this together? This is what? This is a row vector, isn't it? Each one is a row vector. Do you agree? Each one. Well, one second. Each one is a scalar. Each one is a scalar, okay? So you have, as a matter of fact, 1, 0, 0, etc., 0, 1, 0, 0, 0, 0, 0, 1 times A transpose A, x1, xn. Each one corresponds to one of those. plus x1, xn, A transpose A, 0, so 1, 1, 1, 0, 0, minus 2. So this is also 1, 0, 0, 0, 1, 0, 0, A transpose B. Just one thing, this is, transpose of this is equal to that one. Do you agree? This is a number, scalar, right? If you take transpose of this comes here for all of them, and x1, x2, xn goes there. So therefore, this is twice this. There is no need for this one. That is equal to 0. So you have 2 times identity times A transpose AX minus 2 times identity times A transpose B is equal to 0. So identity multiplied with that doesn't mean anything. So what do you have? A transpose AX is equal to A transpose B. In other words, X is equal to A transpose A inverse A transpose B. You see that? Does it look familiar? So the projection of B into the subspace generated by the columns of A is exactly the optimal solution to minimize the error between AX and B. Okay? So this is the proof that projection is a beautiful thing that optimizes that solution. So when you have that zillions of data, all you need to do is just obtain the projection of it. And you don't need to take all these derivatives or anything. Just that projection gives you the optimal solution for your system of linear equation. Okay. Yes?
Can the error be negative?
The error cannot be negative, of course. Why? It is sum of the squares. Right? What if it was complex numbers? Then in that case, norm is defined in another way I'm going to talk about in the coming weeks. Okay? So the length cannot be negative. Length, so when we talk about norms, we define all those. So length has to be positive, and
It's a length, not a displacement.
it's a length. It's a length of a vector. So we also call it in general as a norm of a vector. All those things that I wrote there, now I erase them. All of them satisfy that. All of them are positive, etc., etc. Okay? Okay, let's find the solution of that. Optimal solution of that one, right? That's why we wrote it there. So let's find the optimal solution for x1 and x2 for in that case. So what is A transpose A is what? So it is 1, minus 1, 3, 4, 5, 6, 0, 1, 1, 3, 1, minus 1, 1, 1, into 1, minus 1, 3, 4, 5, 6, 0, 1, 1, 3, 1, minus 1, 1, 1. So that is equal to sum of the squares of this. So 1, 2, 9, 11, 16, 27. Some of you can do better than me, okay? 16. So this is 1 plus 1 plus 9, 16 plus 25. Okay, this is what? Somebody calculate that. And this into that, so 1 minus 1 plus 9 plus 4 minus 5 6, and this is going to be the same. And this is 1 plus 1 plus 9 plus 1 plus 1 plus 1 plus. Okay. So this is equal to what? A transpose A is equal to, what is this? $88. And this is eksi 1, 5, bu gitti, 14. And this is 9, 10, 11, 12, 13, 15. Anyway, so we have to calculate this, etc. I think it's not a good example for a classroom. Okay? So before you leave, come back. Okay, so next Monday, please spread this around. Gel buraya evladım, gel. Bir dakika daha gel, bir dinle beni. Gel, senin için çok önemli, gel. Gitti mi? Okay. As I said in the beginning of today, everybody in this class has to make sure that you learn linear algebra, okay? I cannot just say hell with it. I am just trying every way, any way to make sure you understand this lecture, okay? So I'm going to give you a make-up midterm exam next Saturday. We will fix the time, okay? Sometime lunchtime or something like that, so that they wake up. And next Monday, so not this Saturday, the following Saturday, we are going to have a make-up midterm. But before that, this coming Monday, which day is it? December 2nd? December the 2nd, from 5 to 7, like we did before. Or let's say from 5:30 to 7:30, okay? So it doesn't conflict with the prayer times. 5:30 to 7:30. We will meet in this class. I hope it is available. Yes. And I'm going to solve questions for you. And I'm going to answer questions, okay? Everybody can come. If you take the make-up midterm exam, your current midterm grade will be canceled, okay? So it's not going to be like one of the maximum of the two. If you enter the exam and Ahmed records you, then your first midterm exam will be canceled. Therefore, I'm not threatening you, but you shouldn't take it unnecessarily. But if you didn't have a good grade and you didn't know, and unfortunately, some of you don't know anything about the course so far, and these are the people who are not mostly coming to the class as well. Some of the people who are coming also are not doing well, but if they try a little bit more, they will do well, I'm sure. So tell your friends, they can come to that class, even from other sections, they are welcome to come, okay? Come to class, learn, okay? I beg you, try your best, ask questions. Please take our advice. Try your best. If you fail this course, if you don't learn the material of this course, you cannot be successful in any branch of engineering. This is the basis of many things, okay? So I will see you, if you come, I will see you on Monday. Otherwise, I will see you next week. We will continue with Graham-Schmidt organization process, and afterwards.